The first thing I want to do is look at the questions, the example set questions. So I know you may not have watched the videos, but I'm going to kind of teach as I go here, um, kind of like in context, if you want to think about it that way. So um, the first question, we've got a 2 kilogram block, and it's sitting on a table here or floor or something like that. And it's being pulled to the right with a force F, and there is an angle of 45 degrees here. And then we know that the magnitude of the pull, this force is 10 newtons, and we know that it's going to be pulled across the floor for a time of 0 to 5 seconds. Okay, and that it's going to start from rest, so the initial velocity is 0. And what else do I know about this? Anything else? Let's see. I think that's it. And we have a frictionless surface. So mu is 0. Now, remember I said that, we can't forget about the things that we've learned before. So the first part, or the first question I ask is to determine the normal force acting on the box. And so there would be a gravitational force straight down. There would be this force, the pulling force, up into the right, and then there's a normal force from the floor up onto the object like that. And this is again at an angle, 45 degrees was given. This is my free body diagram, so we can't forget free body diagrams. So our free body diagram gives us a sum of forces. The lights go off in my room automatically, so do not be freaked out. The sum of the forces in the x direction would be this force pull, but cosine of the angle, and that would cause the mass to have an acceleration because there's nothing else balancing the forces, or no other force in the x direction to cause a balance of forces. And in the y direction, we have the force normal is up plus a component of that pull, and that, pardon me, minus the gravitational force will all equal 0. All right, so this first piece is pretty easy. What is the normal force? So we're just going to solve for our normal force. It would be Fg minus the force pull times the sine of the angle. And our object has a mass of 2 kilograms, so that would be about 20 minus 10 times the sine of 45. Okay, so then the normal force should be about 12.9 newtons. Hopefully that's what you got. And so that's part A. So I'm just kind of building up to what's coming next. Okay, so part B, we want to determine the acceleration of the system. So when your net force, the force pull, times the cosine of the angle will equal ma. So that pulling force was 10 times the cosine of 45 is equal to 2 times a. And then we can find our acceleration, and it should be about 3.53 meters per second squared. Okay, so this is all old stuff. So what's the point? Well, so when an object is experiencing a net force, that net force causes an acceleration. Acceleration means that there's a change in velocity, okay? So, and this change in velocity is occurring as it moves through a change in position. So one thing I can do I can relate the change in velocity, the change in position, and the acceleration by going back to kinematics. There was v squared is equal to v initial squared minus, no, plus 2 to a delta x, like that. And so I can write this as v squared minus v initial squared divided by 2 delta x, and that would be my acceleration. So in general, I could write an equation for the net force on this object as being equal to m times this a function, which would be v squared minus v initial squared over 2 delta x. Okay, so we take that sheet here. So we have I'm just going to rewrite this quickly. So v squared minus v initial squared over 2 delta x is what we have there. Now, this force, we're pulling on this object. In this case, the force is not parallel to the floor, but that's okay. Don't worry about that yet. But the force that is causing it to change position is constant. Okay, so if you were to think about maybe a force versus position graph, we would have like this force that's acting on our object over this like change in position. Okay, and we love a graph. Graphs are great because they tell us a lot of information. Now, what I see here is that this force and the change in position, this net force and this change in position, can be related to each other. So I could write this as the net force times delta x would equal mv squared over 2 minus mv initial squared over 2. So this right here may look really familiar. You may have seen the function mv squared over 2 or 1/2 mv squared before. But what's really the essence of what's happening here is that the force that you're applying is causing a change in velocity. So the object went from not moving to moving. It went. The only way you can get your car to go from not moving to moving is to have gas in it, and that gas convert to a mechanical energy to cause the car to go, and that going is evidence that there must have been something transferred. Okay, when you're able to when you plug in a fan and the fan turns and the air blows, like there's a transfer of this stuff that is causing a change. So this, because of the motion or the movement implied by the velocity, this is what we call our kinetic energy. So 1/2 mv squared is known as our energy. And I like to use a capital E with a subscript, just like I do for forces, because I want you to remember it's always energy. It's just stored or manifests in different ways. Okay, so there's not really like different types of energy. There's just different ways that energy is stored. So that means that the work, pardon me, I just blew it there. The net force times the change in position would be equal to this kinetic energy minus the initial kinetic energy. If I have an initial velocity, I'll call that an initial kinetic energy. So then that would give me a change in our kinetic energy. And so this force times the distance, the displacement, if I go back up here, that would be this area under the force position graph, and we call that work. Okay, and the word work probably makes you think of like doing a job. Well, there's a doing there. Even if you go and work out, you're, lifting heavy things or, whatever. And as you are lifting, you are changing the position of stuff. You are moving. There's motion involved there. You get sweaty. There's lots of chemical stuff happening in your body. And the point is to use some of the energy that your body has stored and, convert that to some sort of other form. Okay. So this force delta X is work. So I say all this because in our next part of this question, it says define the system and construct an energy bar chart of the energy transfer during the 5-second interval. Okay, so I know I use the phrase system all the time, but in this case, this is why, this is what's going on here. In this case, I'm just going to have the block. Okay, the block is my system. It's the thing I'm going to look at. All right. So what's happening to the block? Well, the block is being pulled on by a cord. So the cord is outside the system, or whatever the pulling mechanism is. All right. So there's a cord outside of my system. There's an earth outside my system. There is a surface outside my system. And so the block is the only thing in my system. And so the surface could do something to the block. The earth could do something to the block. The cord could do something to the block. Okay. And if I were to really be careful here, it's that the cord can pull on the block. The earth can pull on the block. The surface can pull on it, the frictional force, if there was friction. So by defining my system as the block, all these other things are outside my system. So I'm going to redraw my system because I made a big mess there. All right, so here's my block again. And beep, like that. And so I'm going to draw two axes. And I'm going to say that this one is at t equals 0. And then this one is later at t equals 5 seconds. Okay, so if the block is my system, all right, then initially the block had a 0 velocity, and if energy can be stored or manifest in the motion, then I would have 0 kinetic energy to begin with. And so this graph here, I'm going to put the amount of energy on the vertical axis. I didn't spell that correctly. And then this is going to be like, I don't really like to say type, but the type of energy, how the energy is stored, the storing mechanism. I like to use the word stored because we can transfer it from one place to another. Kind of like when we have water, the water cycle, and it's stored in a lake, it's stored in a water bottle, it's stored in the clouds. It's just different ways that it's stored, but it's always, there and being cycled. Energy is the same way, except for sometimes we have like energy gets stored in a way that is not useful, okay? And so the not useful part makes it is what our issue is as a society. Okay, sorry. Anyway, but later our block is moving because there was an acceleration. So over here at 5, I'm gonna, and this is just a representation, I'm gonna create a bar. Okay, remember like in elementary school when you made bar charts of, how many people have dogs and how many people have cats and how many people have fish, and you did surveys like that. So this is our, I'm just going to fill in a little bit there. So that shows that we go from rest with no velocity no energy to having some energy. Now, you've probably learned in the past that energy cannot be created or destroyed. It can only be transferred, okay? But we just talked about how work causes a change in kinetic energy. And so in this case, with this block, we have this force that's being applied to it. Remember that work is the net force times the change in position in this case. And it's the force that is in the same direction as the acceleration. It's the force that's in the component. So it would be the force that's in the x direction, because you don't want to multiply x force by a y displacement. We know better than that. And so this force is causing work to be done. And so outside my system, remember I put the surface outside the system, and I put the cord and the earth outside the system. And so in this case, the cord is adding energy to the system. And I did 3 blocks, so let me make it look like 3 blocks. That's like an arrow to show that it's being put into the system. So this is the work done by the cord. Okay, and so then this shows me that I have an energy transfer. So whoever's pulling the cord, there's some biology happening, and there's some energy being transferred, whether or not it is a chemical energy or something like that, and it's being transferred. So this the arrow going into the block, just indicates that I have something outside of the system that I have defined is changing my system. So work causes a change in energy. And then if I were to write an equation for this, it would be that the work done by this force pull is equal to the kinetic energy, because everything that happens to the system is equal to the results at the end. Now the question then says, so we did part C, we defined the system, we constructed an energy bar chart, and now we're going to use the energy bar chart to create an energy transfer. Okay, so this is our energy transfer equation. So what I tried to do with these questions was like lots of scaffolding where you could see it kind of take you through. And so then the question is, what's the change in kinetic energy of the block? Well, the change in kinetic energy has to be equal to this work that we've done, and that work would be the force pull that's in the x direction times our x change in position. And so we can determine the force pull. It was like 10 times cosine of 45. Now what is the delta x? Well, earlier we found the acceleration. We know the initial velocity is 0. So we should be able to find our change in position as being 1/2 AT squared. And so we'll put this in here, 1/2. The acceleration we found earlier, which was a number that I can't remember. Now I remember it. I see it. Oh, I'm running out of space. 3.53. And then times, that's times 5 seconds squared. Ooh, ran out of space there, sorry. And that would be the work done, which is the change in kinetic energy. And I think if you do all that mathy business, you get 312 joules. Now, I did in this video or in this session, I didn't go through the units, but if we look back up here where we defined work, work would have the unit of a Newton times a meter, okay? And that's a mouthful to say, Newton meters. I mean, I had a student once a long time ago call it neuters, and we all giggled about that forever. But anyway, so James Prescott Joule did lots of science, and we call it a joule, a capital J for the joule there. And so that's our unit for work. And since work is or causes a change in energy, then energy is also measured in